So let's talk about center of mass, and I'm going to just abbreviate that as COM, so I don't have to write the whole thing out a whole bunch. So say you have got a bunch of objects that you want to think of all together. Maybe I will write out a mass here, and a mass there, and maybe a third mass here. And I want to think of all three of these as one thing, as a system. Well, they all have positions. So say I'll put my origin here. That is where the position's equal to 0, right? And that's where we're going to measure the positions of each of these. So I will measure the position of that first mass, R1. I'm doing it to the center of the mass, that individual mass, R1, center of mass for the individual objects, just as for the system. Here's R2, and there's R3. Okay, so if I'm thinking of these three blue masses as one single system, I need to know where is that system? Where is it located? And that's what the center of mass is. It's the location of where the system is, the position of the system, in other words. And how do we calculate it? Well, the book tells us the center of mass position is 1 over the total mass of the system, so the sum of all three of these masses, and then each mass times its position plus, all the other ones. So mass 1 times its position plus mass 2 times its position plus mass 3 times its position. And there's a little fancier way to write this. We can write this using the sum symbol. So we still got the 1 over the total mass. And then we use the sum symbol, and that just means that we're going to look at each position and each mass individually like this. But instead of writing 1, 2, and 3, I'm going to write I. And I'm going to sub in 1, and then 2, and then 3, and then 4 if I had more and more and more masses, and keep going until I get to the last mass. So that is the number of objects. That is what n is equal to. So this just is exactly the same thing here. For this particular case, n would be 3 because there are 3 objects in the system. So that is what the center of mass is defined as mathematically. And like I said, what it is physically is you can think of it as where this system is. And it's something we've been doing all along. Because, for example, if you look at a pen, you don't think of it as a bunch of different little individual objects. You think of it as one thing. It's just a pen. And you could actually even figure out where the center is. You might do it by balancing. So, for example, let's see if I can balance the pen on my finger. There we go. Right there. That's the center of mass of the pen, where I can balance it, where we think of the pen as being. But, of course, the pen isn't really one object. We can open it up and we can pull out, little tip that holds our finger grippy thing. This is even more objects, but it's a little hard to get the plastic finger grippy thing off. Got the case that has the ink in it and the little metal tip that's got the ballpoint that you write with, and then you've got the base here. So there are at least 3 different objects that all go into the pen, but we think of it as a system. We think of it as just a single thing, with a location right here at the center of mass. And I will note quickly that I'm conflating a couple of ideas here when I say you can just balance it to find the center of mass, but for our purposes, that distinction is not super important. So you can think of the center of mass as where you can balance something. Mathematically, here's how you can calculate where it is. And we've also just discussed how it's an idea that we use a lot. We think of objects, even when they're made up of a lot of things. And of course, we went down a deeper level. This pen's made up of atoms and molecules and stuff like that. But we don't think of individual atoms and molecules when we're doing any physics trying to figure out what this pen's going to do. We just think of it as a single object. But we've also been using this center of mass in another way. So what would happen if we took the time derivative of this equation? So we'll take the time derivative on one side and the time derivative on the other side, because of course you always got to do the same thing on both sides of the equations. I'll try not to get too sloppy with all my letters as I'm writing them. This is going to be the total mass again. Okay. Well, here we're taking a time derivative of a position, so that's just a velocity, and I guess it'll be the velocity of the center of mass, or the velocity of this three-mass system. And then here let's make an assumption, which let's assume that the mass is constant. It's not always constant, but generally it is. And if the mass is constant, then this mass will just come outside of the time derivative because it won't change in time because it's constant. And then here we can actually then move the time derivative inside this sum. And that's okay to do because we are summing over the number of objects, but we're taking derivative with respect to something different. We're taking derivative with respect to time. So as long as this is a sum and that's a derivative of different things, you can move the derivative inside the sum. So I'm going to go ahead and do that. And then according to our assumption, mass is constant, so that mass is also constant. So the derivative just moves inside of that without changing it, and we are left with just this guy. The derivative of each individual position with respect to time. But that, of course, is the velocity of each individual mass. Now if I multiply by the total mass on each side, I'll have my total mass times my center of mass velocity equals the sum of all my individual masses times all the individual velocities. And this again is an idea that we've already been using because this is the sum of all the individual momentums. So we look at each individual momentum of each individual object and we say that is equal to the momentum of the system, which apparently is just the total mass times the velocity of the center of mass, the velocity of where we're thinking of the system, if it's just a single object, where it would be. And so that's one reason why we like the center of mass. It means that we don't have to think of, say every individual atom in an object and figure out what the mass of each of those atoms are and where each of those atoms are located and do all of the math on all the individual atoms. Instead, we can think of all the atoms that have gone together to, say, make up an object like the pen, and just think of the pen as one object itself, an object that has a location and a mass. The location is the center of mass, and the mass is the total mass of all of the little things that make up this system that is the pen. And you'll notice it's also a vector, and so that means that this equation is actually three different equations. This equation is the x equation. So the x component of the center of mass, it's the total mass over the sum of each individual object and its x position. And the y component of the center of mass, it's the total mass and the sum of each individual mass and its y component of its position. And the z component of the center of mass, it's 1 over the total mass times the sum, oh, not a very good sigma there. There we go, that's a little better. Times the sum of each individual mass and each individual object's position. Now notice that it's the same total of mass for each of the components because mass, of course, is not a vector, it's a scalar. So we do need to use the actual mass for each component, but we can split the vectors, these position vectors, up into their x, y, and z components. So whenever you're trying to find the center of mass, go ahead and split it up into pieces like this. The x piece, the y piece, and the z piece, and that'll make your life a lot easier.